So this is a micro tutorial on my first analog integrated circuit. And what's this about? This is intended for pretty much anyone who has designed circuits in the past and would like to know how to design an integrated circuit. It's mostly about analog ICs, but also we can talk about a little bit of digital, mixed signal, RF, some other circuits. And this is going to be an overview, very shallow description on how to make a chip. It's not, well, you'll see what to expect after this. So, all right, I'm an accomplished circuit designer. I have designed lots of circuits, right? I know how to design discrete circuits. Yes, I'm familiar with all these, right? And I have laid out many PCBs. I hope this is your case, right? And I know about fabrication procedures for PCBs, and I know a lot about components, right? So this, I hope, is your situation. But I would like to know how to design my first chip, how to move everything I've done to a single piece of silicon. So this is basically what we want to know about in this presentation. So why should I move my design to silicon? Because it's cool, definitely. It's cool to say I design chips. And it's much smaller. You can make things really, really small and much higher performance. It's faster, it's lower power, low noise, more precise in terms of the signal. And also it's much cheaper in large quantities. And we also have much better models for integrated circuit design. If we design a chip with components off the shelf, we usually use macro models, which are not really accurate sometimes. And well, also because designing chips is not rocket science. I'll show in this presentation that anyone can design a chip. So this is what you should expect from this tutorial. You won't become an accomplished IC designer. This isn't deep enough, this isn't thorough enough. But you will learn a few things. You will learn how to begin with IC design, and you will have some interesting conversation topic for a nice family conversation. I used to talk about the chips in my family. They hate me about this. But anyway, who I am. I am an assistant professor at a university here in Chile. I got my PhD in microelectronics, and I got a degree in electrical engineering. But above all, I am a nerd, and that's what describes me best. I'm a nerd, and I like building stuff. I like taking things apart and learning how they work. And well, I think that's what got me here at the end. All right, so this is the tutorial outline. We will talk about a little bit of history here. I'll be ashamed because there's a person in the audience who knows way more than I do in this. But anyway, background, terminology, classification, fabrication processes, components, libraries, design flow. I'll say a few things, just a few things on circuit design, some layout guidelines, design tools, fabrication services, and some more resources in before 5:30 p.m. So it's going to be really fast-paced. A bit of history. Not long before the IC, there were discrete diodes, transistors, inductors, resistors, capacitors, etc. And you know, we all hand soldered them to PCBs. The PCBs are good substrate for circuits. It holds the circuit mechanically and provides good electrical connection. The problem with PCBs is that the assembly processes do not scale well with number of components. If we have too many components, it takes too much time to build a PCB. Surface mount devices has made this a little bit better, but still, it doesn't scale that well. PCBs are large and are full of parasitics, and parasitics degrade the performance of our circuits. Also, the PCBs are expensive. Why? Because we pay for each component. Each capacitor, each resistor has a cost, and that's why PCBs are expensive. That's not what happens with ICs. So circuit design was at the time done at a very low abstraction level using basic components. There were no complex building blocks. Then in 1958, the IC was invented. Jack Kilby at Texas Instruments. He fabricated the first IC. He was working during the summer. He made this during a summer, and a few months later, a completely unrelated work, Bob Noyce from Fairchild Semiconductor fabricated another IC. They they have a few similarities and a few differences. Kilby's chip had embedded passive components. Bob Noyce solved the interconnection problem, so he had the metal lines in the chip. In this other case, Kilby had wires. Then the IC became practical. In the 60s, we had small-scale integration with a few logic gates per chip. Then in the late 60s, they went to MSI, medium-scale integration, mid-70s LSI, and now we are in the very large-scale integration or ultra very large-scale integration. They call it different ways, but I prefer this term because I think it's more general. Currently, they have built more than 10 to the 9 components in a single chip. Way more than that, actually. So we now come to Moore's law. This comes from a paper from 1965, where Moore took a few points of data. Here we have just a few of them, and he predicted that if the trend continued this way, basically the increase in the number of components per chip followed an exponential law, and it doubles every 2 years, basically. Or I would say now it's 1.5 years. This was not all digital, right? There was a lot of analog IC in that time, in the 60s. Here's Bob Weiler, probably the father of analog IC design, because he designed many of the first integrated circuits, first ever integrated circuit. First op-amps with internal compensation. He did a lot of work in bandgap references. First high power voltage regulator, and so on. He designed many interesting stuff. So this was not only digital. Electronic design at that time was handmade, so there were masks, and these were cut by hand, basically. Then they moved to computer-aided design, and then there came the Mead and Conway revolution. This came in the 80s with the book Introduction to VLSI Systems, and this began what we think now was a revolution, because IC design was something that anyone could do at the time. There also began this multi-project chip and multi-project wafer services, like MOSES services. Who is familiar with MOSES in this room? Okay, who have worked with MOSES? Okay, gives me an idea. Okay, so then the commercial EDA software appeared and HDLs were born. So here we see a chip that has many projects in it. Here's a chip, here's another chip, and so on. Okay, this section is about background, what we would like to know on terminology. Okay, so we have a discrete circuit here. We all know what a discrete circuit or circuit with discrete components is. It has integrated circuits. It has passive components. lots of passive components. A hybrid circuit has integrated in a single PCB many components, but it can be considered as a single piece of, circuit. So this is a block as opposed to this one, which is made of different blocks. This is a complete block. And an integrated circuit has all components integrated in silicon, in a single piece of semiconductor in general. I will talk about silicon because for a first IC, I think it's the right decision. So this is a chip. Actually, I have some chips here. If we have some time later, I'll show a chip under a microscope. So about processes and technologies. There are main fabrication technologies: bipolar, CMOS, bi-CMOS, which is both bipolar and CMOS in the same wafer. And why CMOS is so important right now? It's because it is a highly developed technology. It's driven by digital circuits, but it is also suitable for analog and mixed signal design too. It is cheap and it has great performance. So that's why we will talk mostly about CMOS in this tutorial. So this is a first order comparison between MOSFETs and BJTs. CMOS has a high gate resistance. The BJT doesn't have that very high gate resistance. CMOS is a great analog switch, right? It's great for switch capacitor circuits and that kind of technologies. CMOS is also perfect for digital gates. It's cheap, it's small, and there's so many fabrication options. BJTs have a much better transconductance per unit of current, have usually better gain and better noise performance. In terms of speed, they're both really fast. So this shows, this plot here shows technology nodes and scaling. When I mention technology nodes, this is a terminology for IC design. We refer to the transistor length. This is usually for CMOS devices, and we say this is a 130 nanometer node, 130 here, which means that the smallest feature that I can fabricate for a transistor is the length of the transistor, right? The channel length is 130 nanometer. So each one of these points shows a technology node. And this axis here shows the year. And we see how this has been moving really fast. Every time we move from one node to another, we scale the dimension in alpha. So alpha is the dimension scaling. Every time we scale in alpha, the length changes to 1 over alpha, right? The width of the channel width, changes in 1 over alpha. The area of a transistor, which is given by the product of these two, changes in 1 over alpha squared. And if we do this scaling in constant field, which is no longer really used, but this is what if we could keep scaling in constant field, we would get an improvement in speed of alpha and improvement of power efficiency in alpha square and in energy of per operation in alpha to cubed, right? It's a huge increase. It's amazing, and that's what allows me to give this presentation without any power. All the power is in the battery, right? This is possible because of this square here, of this cube here. Okay, so this is mostly about technology nodes. So I'd like you to hold this concept of technology node. Let's talk now about analog mixed signal circuits in CMOS processes. CMOS is, as I mentioned before, intended mostly for digital circuits, but we can also make analog and mixed signal circuits, right? Transistors are really good amplifying devices, and we can use them for that. We have high resistivity materials that we can use to make resistors. We can make parallel plate capacitors. So we have components. We can make spiral inductors. So it is possible to have RF circuits in a single chip. So if we exploit the CMOS advantages correctly, we can make circuits that are really, really complex. We can have entire systems on a chip. What's this design flow? Because if we want to design a chip, we have to go over a certain number of steps, right? So the design flow is the set of steps and procedures to design an integrated circuit. For example, a very simplified design flow would be first design the circuit, synthesize the circuit, then have the place and route, then have the verification done, and that would be a design flow. The design flow depends on the design tools, the type of circuit, if it's an ASIC, if it's a custom IC, if it's analog, digital. It also depends on the process. We will talk about this later. About the fabrication procedures, we usually submit the chip to the fab. We call this a tape out. This is the tape out process. So we usually email the chip, email a single file with the chip. We can use FTP, HTTP, whatever. It takes 8 to 12 weeks. Then the chips are diced from the wafers, and then they are bond wired and packaged, and we end up with a chip like this. And this we can put it in a PCB and test. About the EDA tools, electronic design automation tools, they can do a lot of things. Circuit simulation. Who has simulated circuits here? Who uses SPICE? Any version, any flavor of SPICE, right? A Spectre RF, good, very good. Eldo, good. So there's a lot of tools, right? So circuit simulation. Then we have a schematic capture, which is usually related to circuit simulation. We have layout. We can do layout for PCBs. Who has done layout for PCBs? Most of us, right? And we can do layout for ICs, which is pretty much the same thing. Moving from PCB to IC is not that different, okay? There's synthesis tools, place and route tools, and verification tools. And there's a few developers here, Synopsys, Cadence, Mentor Graphics, Tanner, and there's free tools too. So if you cannot afford any of these mainstream developers, you can use Open Circuit Design. If we have some time, I'll show a demo on open circuit design. All right, about models, libraries, and PDKs. We have to get used to all these terms if we want to design a chip. Models are required for design and simulations. If this is something I learned when I was at Stanford. If you don't simulate it, it won't work, ever. If there's something that you do not simulate, that part will not work, because that's how Murphy works. So it's very important to do all your simulations. And if you want to simulate properly, you need models. You need something that models your transistors. So you need libraries with all these models, right? So you usually get libraries that include standard cells, logic gates, models, IP, cores, for example, data converters, amplifiers. There's many providers. There's a big market on it. Usually, part of this, or even standard cells, are included in the process design kits, PDKs. So when you want to get involved with the design for fabrication, you first begin with a PDK. You require a PDK for a certain program. Each vendor provides PDKs for different EDA tools. For example, if you decide to work with Synopsys, you need PDKs for Synopsys. If you decide to go with open circuit design, maybe you can find some free PDKs. Not all EDA tools are always supported. For instance, only a few processes support Mentor graphics. So if you want to go with Mentor, you can't choose any process. NDAs, non-disclosure agreements, are usually required to be signed in order to obtain the PDKs. This is really sensitive information, and this is something you can just disclose. That's something that, as PCB designers, sometimes we're not used to that. We say, okay, this is my IP, I send this for fabrication, I don't want anyone to copy this. But when you get a PDK, whatever files you get in the PDK are very sensitive information and uh, must be kept with a lot of care because of that. Typical IC. This is a complex 3D structure. For those who are not familiar with ICs, this is a wafer. This is a cross-section of a wafer or a chip. This is the substrate. Over the substrate, we have transistors, and then we have lots of metal layers. Usually, it could be up to 9 metal layers. Most of the examples I'll give during this tutorial are for a 0.5 micrometer node. So we'll go back here. 0.5 micrometer. 0.5, it's about here, right? So it's a pretty old technology, but it's great for learning purposes. And it's free too. I'll say more about that later. Okay, but we use a 500 nanometer. And in that process, we have 3 metal layers. So we can do exactly this with 1, 2, 3 metal layers. And we can make capacitors, resistors, inductors, and transistors. Some differences between discrete and integrated circuits. In a discrete amplifier, we want to minimize the number of transistors because each transistor is expensive. So we have here only 3 BJTs, right? In an integrated amplifier, we have way more number of transistors because each transistor is free. Basically, in a wafer, in a die, an extra transistor doesn't cost anything. So we have unlimited number of transistors. And I design my devices in an integrated amplifier. I design the shape of the transistor I want. I design the shape of the resistor I want. I control the mismatch. If I want two devices to look exactly the same, I can do the calculations to make them exactly the same. Well, you can never reach an exact similarity, but you can control that. So you can control mismatch. But you have a smaller range of integrated resistors, capacitors, and inductors too. Okay, about CMOS processes. Again, why CMOS? Because it's the most developed IC technology. It's the one that's driven by digital IC design. It's really cheap, and it has great performance. So what defines a CMOS process? As I said before, it's the technology node, which is given by the gate length. So in a transistor, which we usually draw like this, the technology node is the length. So we say, for example, 180 nanometer. That will be the technology node. We have options over a CMOS process. If we have a digital process, that's intended for transistors, right? NMOS, PMOS transistors, and wire interconnects. But we can add some options like high voltage transistors. You can have up to 200 volts in a chip with very high voltage transistors. The usual is a few tens of volts. You can have special capacitor layers to have very high capacitance in the chip. You can have high resistivity layers, and you can have some other options. So let's find out about integrated components. This is a MOSFET structure. Hope most of you are familiar with this. So we have here the substrate. We have these diffusions. This is usually a P substrate with N plus diffusions here. We have the gate oxide here. and we have the poly for the gate. Actually, MOSFET, you know what MOSFET means? uh, metal oxide semiconductor. So it will be metal oxide semiconductor field effect transistor, right? This is no longer made of metal. Most are made of polysilicon. So we should change that to POSFET, but that wouldn't be that cool. So we keep saying MOSFET, okay? But it's poly. So it's a polysilicon gate which has a low resistivity, not as low as metal, but still we use poly, and it's very convenient for fabrication. And we do have metal connections to the different diffusions. Okay, so we have gate, drain, and source here, and we have the body. Usually we draw this like this, and we say, okay, this is the source, right? The source, which is shown by this arrow here. But the device is actually completely symmetrical, isn't it? I don't see any difference. So I could say S, D, and it would be the same thing. It's exactly the same thing. As opposed to BJT, MOSFETs are completely symmetrical. All right, so we fabricate MOS transistors over a substrate. The wafer is typically a p-type substrate. So here we have p-type with a moderate low doping level. So it's a highly resistive material. And we can make NMOS devices immediately on top of it. So we have N plus implants or diffusions. And then we have an NMOS device. Here is an NMOS device. So where's the body connection here? I don't see it. Does anyone see the body connection? To the left, right here. So this is the body of the chip, of this transistor, which is shared among all NMOS transistors. To the right, we have a PMOS device. So this is a PMOS device. PMOS devices are made of P-type implants over an N-type wafer, right? But this is a P-type wafer, so we need something in between. We need to create an N-well. So this N-well is a part of this wafer which is changed. So instead of looking as a P-type, it looks like an N-type material. And on top of it, we have these P plus diffusions or implants. And then we can have a transistor. And this would be the body connection here. So it's actually this is N plus for a connection. All right, the details of this I can't give because we don't have much time. So I want to I want to go a little bit fast-paced. MOSFETs in large signal. This is a completely qualitative, I would say, classification of the different operation regions, right? So we have cutoff, active or saturation, triode regions. And there's another, which is sub-threshold. Who has designed any circuits in sub-threshold operation? Good, good, very good. Yeah, so this is the most common. This is what we usually teach in basic electronics course. But this is a very important region because here you have a lot of power efficiency. And even though the performance is not that good, for very fast transistors, you can make a very good performance, very fast, very low power circuit here in sub-threshold. So we all know in cutoff we have the transistor off, switch open, high resistance, no current. Active or saturation is good for voltage controlled current source, so we can make amplifiers. And in triode we have a switch that is closed, right, a low resistance, and we can use that transistor in triode as a capacitor too. Well, here are the equations. We all know this, right? And here we have the curves for the MOSFET transistors, right? We won't talk about sub-threshold now. We will mention that later. So here are the basic equations. We all know that. And small signals, well, this is the basic model. So we usually take this as a transconductance and output resistance. This is due to the body effect. Sometimes we just omit this from the model. This is a pi model, but we also have the T model. We can use either. This is the equation for the transconductance. And all these equations come from here, from this equation here. So this equation here, we would call it the the typical way we call it is a square law model, but we can also call it low field transistor because it's good for low electric fields. And here we have a very rough, not very good equation for output resistance. We usually don't use this equation very often because it gives awful results. But anyway, so how can we design with such a bad equations? We will show later. So here's a MOSFET transistor. This is the device, P-type wafer with N plus diffusion, N plus diffusion. We saw that this is poly, and this one here is oxide, some kind of dielectric layer. And this is a transistor, and this is the body connection. And how do we lay this out? How do we have this transistor in a CAD for design and fabrication? So this is how it looks like. It's exactly the same thing. It's diffusion here, then we have a poly here. This is the gate. Then we have a contact from the poly to metal. So this is metal 1. This is the first layer of metal. We have a contact here from the diffusion to the next, to another metal layer. So this is metal 1, 2, metal 1. And this is our transistor. That's it. That's how we draw a transistor. So which would be the length of the transistor here? Would it be this here? No, right? So what's this here? That's the width, right? And here we have the transistor length. Okay, this is exactly what we draw. If we want to make a wide device, we just make it wider. That's it. And we can draw it by hand, basically. I'll show a few examples later. PMOS transistor is the same thing, but now we have to add this extra layer here. So it's a different color. I don't know if you all can see it, but what would be this extra layer here? This is the N well, which I mentioned before. We need for PMOS devices. Okay, so this is the N well. Over the N well, we have the P-type diffusions, then we have the gate, and we have a PMOS transistor. And we need a connection for the body, so here it is. Resistors. So resistors are usually made of high resistivity material. It's simply, could be metal, but metal is not very high resistivity, so we use polysilicon. Polysilicon has an implant that makes it really low resistivity. So we need to block that implant to prevent that from being low resistivity. We use silicide block, which is something that allows us to create high resistivity material. In IC design, we can draw our resistance the shape we want. So if we have, I don't know, transistors here, and we need some resistance somehow, we can put it like this, any shape. And oh, we need more resistance. Yeah, we can make it that way. It's okay. We can make it the shape we want. So how do we compute the resistance of a weird shaped resistor? The way we do it is through a concept called sheet resistance. So sheet resistance is for a constant thickness material, so a material that has a relatively constant thickness, that's the resistance of a square of material. So if if we have a square of material with a constant thickness, and if we put an electrode here and another electrode here, and we measure resistance, if this is a square, that's the sheet resistance. So the first question is, what dimensions of material? Because I could make a square like this, or I could make a square like this. Do these all have the same sheet resistance? Yes, because the sheet resistance is a property of the material. It depends on the thickness, but doesn't depend on the size of this square, because if we increase the square, we increase the length, but we increase also the width. So we keep the same shape, basically. And how do we compute the resistance of a certain shape of resistor? Well, we count squares. For instance, we can have something like this. And we count 1, 2, 3, 4, 5, 6, 7 squares plus a corner. Corner has a different sheet resistance. I think it's 0.56 or something like that. So this would be something like 7.56 squares of material. And if we know that we have 1 kilo ohm per square, so this would be 7.56 kilo ohm. And that way we can design any resistance, any shape we want. Then you might ask, well, if I want to save room, we could do this with smaller squares, right? We could do exactly the same thing with smaller squares. Right, but then you can't have much current on it, so there's a minimum you can have. Also, when you make small squares, you might end with some low precision problem, because these squares are very small, and you can't count on the sheet resistance for very small squares, because a small square actually looks like this, and you don't know the resistance of that thing. So if you make it bigger, you get better precision. We will talk about that later if we have time. Integrated capacitors. Well, a capacitor is just two metal plates separated by a dielectric, and that's it. So we have metals in a chip, right? We have this metal, we have this other metal, and then we have a parallel plate capacitor. That's it. That's how we design capacitors. So this would be a poly, this is poly, insulator, poly capacitor. This is a PIP capacitor, poly insulator, poly. We have MIM capacitors too, metal, insulator, metal. We have MOM capacitors, which are like this. So we have here metal, here we have the other metal, and in between we have oxide. So this is a MOM capacitor, which is a lateral field capacitor. And there's many flavors, many ways of making capacitors. So you can actually make a capacitor by just running two lines very close together. And there's some advantages, some disadvantages of each. For example, here we have a very high capacitance to substrate, from this plate to substrate. This one has a much smaller. So if this capacitor is size C, we would say this could be about 0.1 C, and this one could be 0.01 C. And we have to take this into account, because these are important for the performance of our circuit. Inductors. We have inductors too. This is a chip we designed just to measure inductors. And we have here just connectors to the pads, right? So here's an inductor. It's just a spiral inductor. There's many ways of making inductors. There's a great book on that. And this equation comes from Professor Lee book. This is basically what number of turns we want for a certain inductor. This is the winding pitch, which is turns per meter, and then L is the desired inductance. There's many more design equations like this for different shapes of inductors. This is a basic square inductor. Okay, we'll say a few things about design flow. So we'll show a video. This is in Spanish, so I will say about this video a few things. So the first thing we do is design the circuit. We begin with a transistor and we pick a topology, and we get to a topology, we do calculations, we size the transistors, we give currents, and we end up with something that we like. Then we simulate that. We go on Spice or whatever other software we want, and we do all kinds of simulations to make sure that this is going to work. Then we go on the layout. We say, okay, we begin with the transistor, right? And we place more and more transistors and more components until we get an integrated circuit. This was designed by one of my students using free tools, actually. We have a complete layout, 1.5 millimeter each side. Then we verify the circuit. We want to make sure that these two are exactly the same. So we run through through a program that will do that. Then we submit for fabrication. Takes a couple months. And then we come back with the actual chip. And then we need to characterize the chip, right? So we build a PCB, and then we put the PCB, a chip in the PCB, L chip, right? And then we want to test the chip. So we connect it to our testing equipment, and we make sure that this works fine. And this, of course, can be used in many kind of applications. Okay, that's not very important. This was done by my students, so the credit is for them. But thank you so much. So first part, circuit design. So how do we do that? We need to pick a topology, and now if we're working with transistors, we can't just put an amplifier there because amplifiers are made of transistors, and we have to design the amplifiers, right? So we need to carefully choose the topology. In this case, it's this topology. We have to run behavioral simulations to make sure it's going to work. Then we do all kind of hand calculations and optimization. Then we implement the circuit in SPICE, and then we iterate many times until we come up with a circuit that will work. And this is what we end with, a schematic or a netlist, a list of components interconnected that will tell us electrically what we expect from the circuit. Then we go over layout. Layout is the physical description of each one of the chip components on every layer. Sorry, there's many programs that will do layout. The output format is a GDS2 file. And this is a layout of a chip, and if we zoom into this part, we have this, and if we zoom into this part, we have this. It's amazing how much information, how many building blocks you can make. It's amazing. For this 1.5 millimeter chip that we showed in the video, if we consider each one of the building blocks a Lego piece of 1 centimeter long, the chip, the 1.5 millimeter chip, would be 50 meters long. 50 meters by 50 meters. That's amazing how you can build so many things in such a small piece of silicon. So I hope if you have not designed a chip, I hope this will make you think about it, because it's not that complicated. You can make it. Pad frame. So the chip, the core, here's the core. The core of the chip is connected to a pad frame. This is the pad frame. And it has many different kinds of pads. We have VDDs, for instance. We can have a VDD here. And this VDD is shared among all parts of this pad frame. So if you want VDD, you connect to a pad frame anywhere where you have a VDD connection. Then you have ground. For instance, we could have this one ground. This is just for example. I don't know if this is a ground path, okay? But if you connect ground, then ground is shared among all paths. And if you need ground here, you just connect it there. And there you have ground. We have analog paths, which are just a wire between here and there. It's a wire, nothing more than that. It also has some protections. We need those protections to make sure it will hold ESD, right? So that's an analog path. We have digital input paths that have buffers, so you have something like this. This is a digital input path with protections too. We have digital output paths, which is the same thing, but the other way around. It has buffers. So you come here with a very, very small gate, and you can drive here a TTL circuit. We have NC. NCs, where are NCs? Here's NC, right? Here's non-connection. You don't connect that. We have corners. These are corners. We have spacers. Some of these are spacers too. We use spacers when we want different VDDs on a chip. For example, if we want to have a VDD for analog and a VDD for digital on a single chip, we put spacers here that won't connect this VDD with this other VDD. And that way you can make a circuit with many sources of voltage. Okay, and each one of these is a path, and you get that from PDK. What are PDKs then? Process design kits, right? So you get them from the manufacturer. Okay, how automatic is layout? If you do analog, it depends on the program you use. Simple programs will just draw, you just draw by hand each transistor, each part of each transistor. You just draw rectangles. In more advanced programs, you can say, okay, I want transistor this size with this number of fingers, and I have the transistor right here. And you can make some other kinds of automations with more advanced programs. You can instantiate custom or standard cells, and you can do a schematic-driven layout, which is something that we used to do also for PCBs. When we have a schematic and we want to make the PCB for it, the program will check if it's electrically the same, right? We do the same for IC design. So there are programs that take care of this, that will make sure that your layout looks the same as your circuit. And you can also use automatic routing. In digital circuits, it's much more automatic. You just describe what you want the circuit to do, and after a few steps you have this, which I don't know what it is, but I know what it does, right? So this is a synthesis followed by a place and route tool, and you can tell the tool, I want about this size, and the tool will make sure that your core fits in this size. This is a quick example. This is a very, 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 very suboptimal amplifier, okay? So what kind of amplifier is this? Okay, this is a clue. Here's the amplifying device. This is a transistor. This is current mirror, right? So these are two PMOS transistors connected as diodes just to have a voltage here. And then we have this current mirror here, so this will be a current source. And then we have the load here, and we have here a resistive voltage divider, which just sets the bias point here. And we have this capacitor, which we use there for what we use that capacitor? A coupling cap, right? That's a coupling cap. So if we want to couple only AC signals, but not DC signals, we want a very large capacitor here. This is basically a high-pass filter. And then we have another capacitor here, which bypasses this current source. So this is a bypass capacitor, right? Bypass capacitor. And we see this layout, which is exactly the same as this thing here. And we see that the amplifying device is this. And then we see that this current source is this device here. And this one here is there. And the two PMOS devices are here and here. This resistor is here. These two resistors are here. And whoa, huge capacitors. They use a lot of circuit area, right? I don't like that because that's really suboptimal. Usually we don't put many capacitors or resistors in a chip because they take up so much room. This is just for example. Um, there are much better ways of doing this circuit without so much capacitance, for instance, going differential and not requiring this and possibly getting rid of this too. But this is just to show how much room it takes for a resistance and for a capacitor in a layout. And I made this layout this with this form factor, but you can make it any way you want. This is fully custom. So if we zoom in, there we have the transistors. This is this one here, these resistors here, and then these two are these two here. So then we need to verify the chip. And the verification has many steps, at least I would say 3. The first one is to make sure that the design rules that the fab gives us are not violated, right? So this is the design rule check. This is provided by the manufacturer. And this tells us what sizes, what dimensions, what space between lines we should hold. And if we don't observe these rules, we come into a violation that might render this chip with very low yield or non-manufacturable. So we want to make sure that we pass all design rules. Then we have the LVS, layout versus schematic. So what we do here, we have this layout here, and we tell this program, I want to know what circuit this is. So the layout will examine, the program will examine this and will say, this is a capacitor, this is a resistor of this size, this is another resistor, and these two are actually connected this way. And so the program, which is the extraction program, will extract all the information from the layout and will try to say what's in that layout. So it will give us a netlist. So after we do the extraction, we end up with the netlist. And this netlist might include parasitics. And then we have a program that will compare this netlist to our schematic and will tell if there's any differences. Usually they are. There are lots of them. It will say if there's a mismatch in the number of nodes, in the number of components, the size of the components, and then we can debug the circuit until we get a perfect match. So once we pass LVS, we are sure that what we wanted to make is what we are actually sending for fabrication. We have to do antenna rules too. So this is a third part. Antenna rules are to make sure that charge that is accumulated during the fabrication process won't break the transistors. And then we do a post-layout simulation, which means that I take the extracted netlist, the one that we extracted here during the layout versus schematic, and that netlist is something like this, just a netlist, right? And we put it into SPICE, and we simulate the chip. And if it works, then we are kind of sure that it will work in practice. If we do the simulations right, we don't want to tweak things to make it work. We want that to work in any condition. So we want to make sure it works for a fast process or a slow process or a typical process. Usually the fab gives us process corners, what we call process, for instance, a fast NMOS device and a fast PMOS device or a fast NMOS and a slow PMOS, we have many options of process corners, and we want to simulate this in all process corners to make sure that this will work fine. Okay, so this is the design flow summary. We start with the specs. We get a system level design, architecture, circuit design, which gives us a netlist or schematic. Then we implement the circuit, we get a layout, and then we verify the circuit. If it doesn't work, we come back again. And we do this as many times as we need to make sure the circuit will work. Okay, so we have 1 hour left. I will not say many things about circuit design, but I will say a few of them. This is analog circuit design. So this is my first analog IC, right? So this is why we will talk mostly about analog circuit design. This involves topology selection, element sizes, current biasings. So this tutorial is not on circuit design. There's many great books on this. So we will not cover this. Usually it's not easy, but it can be learned in a single semester, actually. It takes years to master, right? But you can start knowing nothing about this, and at the end of a semester, you can have an operational amplifier design. Oh, sorry about this. I'm terribly sorry. So this is something that where I was at Stanford, my professor told me, it's amazing how in one semester, students knowing nothing about this end up with a fully functional operational amplifier. And I tried this in Chile, and it works too. It really works. So this is not on circuit design, okay? But we will say a few things that can be useful. We'll also talk a few things about gain, bandwidth, noise, mismatch, feedback. Okay. As I said before, some say that it's a dead art, some say it's black magic, but it's not. It's something that you can do systematically, even though tools won't do it very easily, but there are some tools that actually make easy to work with systematic analog design. The outcome of this is a custom, fully custom, unique block that you can instantiate anywhere in the chip, right? Most blocks, A to D converters, D to A converters, LNAs, mixers, whatever, most of them use amplifiers. So we will talk about the amplifier as the basic block of analog design. So what amplifiers? There's many kinds of amplifiers, right? But we would talk about operational amplifiers that work with voltages. Input voltage and output voltage, okay? So input is a voltage, output is a voltage. Most amplifiers fall in this category, so it's fine. Probably we're all used to this. And we do feedback through some passive components, right? And the feedback will control gain and make some other very good things like, well, we can talk about that later. Amplifiers allow to implement a wide variety of blocks, as I said before, A to Ds, D to As, filters, regulators, etc. So we'll take a look on amplifiers. So how do we design? We first define the specifications. We validate them through behavioral simulations using MATLAB, Scilab, Python, whatever we want to use. Then we come up with or pick a suitable topology made of different subblocks, right? And we calculate all important figures of merit. Then we establish the transistor's operation points, and we want each transistor to be in a certain operation point. We simulate a lot. That's very important to make sure that it's going to work, and we iterate many times as necessary. So the specs might include many things. The typical, we would say, is open loop gain and bandwidth. We have power consumption, we have feedback factor in a closed loop, phase margin, input referred noise, input common mode range. There's many of these. And sometimes we care a lot about some of them. Some other times they are not that important. So once we have the specifications, we have a great part of the problem solved. Then we come up with a topology and we want to compute the gain of this thing. So how do we compute the gain? Well, I know that this transistor is working in active mode, so I know ID equals 1 over 2 times mu COX W over, we know the equation, but how do we compute the gain of this thing? It has so many transistors. Yeah, it scares me a little bit. So we will try to find out a way to compute the gain of that transistor. So what's in an amplifier? Any voltage amplifier operating in a linear regime in a certain band of interest can be modeled as this: a transconductor that will convert voltage into current, and then a resistance that will convert current back into voltage. So it's strange that if we want to amplify voltage, first we convert it into current, then we go back to voltage. But that's the way it is done. Okay, and we compute the gain. So if we have GM times VI, where VI is the input voltage and this is VO, so VI, then GM, VO, and we would say that the gain in this case is VO over VI, and it would be minus GM times R naught, right? So usually that's the gain. The GM of the amplifier times the R naught of the amplifier. This GM is not the GM of any of these transistors, okay? So that GM is the transconductance of the whole amplifier. So we can define an effective transconductance for an amplifier and an effective output resistance for an amplifier, okay? And we can come up with something like this. Okay, so we could get the GM of this thing and get the R naught of it, and we could get to some kind of gain, right? So we could do that, okay. Example, common source amplifier. So we begin with this, and we suppose this is in active region. So we can go to a small signal model. So what's the small signal model of this? Well, we know the transistor is just a transconductor with GM times VI in this case. We have the R naught of the transistor. We have the RL, which goes to VDD, but VDD in small signal becomes what? Ground. Very good. So we go to ground, and we have VO here, and then we have that the gain is simply GM minus GM times R naught in parallel with RL. And that way we compute the gain of this small block. We can do that for more complicated blocks. Okay, so how do we compute the gain in this case? And the key concept here is divide and conquer. We cannot simply look at this and compute the gain, so we need to start looking at blocks, and maybe this is something that I could understand, and maybe this is something I could understand, and then separating this into blocks, maybe I could compute the gain. In fact, it's not that complicated. So the building blocks are just a few of them: common source amplifier, common gate amplifier, common drain amplifier. And there are some other useful configurations: current mirror, differential pair, active load, cascode configuration. We will mention a few of them. Common source amplifier is a very good transconductor or voltage amplifier. It has a very high input impedance, right? It has a relatively high output impedance. It has a GM of the transistor. The effective GM here is the transistor's GM, and the gain is minus GM over times R naught, right? So we know how to model this. This is exactly what I showed before. GM R naught, and this is GM times VI. This is VO. That's it. And we can compute all this from the small signal model. Common source amplifier with source degeneration. It has a more predictable transconductor or voltage amplifier behavior, right? So this is feedback. At the end, this source resistance act as a feedback that will make it much more controllable GM. So GM effective is not something that depends much on the transistor, right? In this case, when GM times RS is large, this is almost GM over GM RS. And then this is equal to 1 over RS. Then we can control the effective GM of this amplifier just moving RS. Same thing with the output resistance. It depends on RS too, and then we can have a gain that could be GM times R naught if we multiply these two things when RD is infinite, or we can have something that is fully controlled. Again, in this case, it's fully controlled by RD over RS. So this is a really handy equation if we want to design very quickly transistor amplifier. We just put a resistance here, another here, and then we have the quotient of that is the gain. That's it. Okay, common gate amplifier. So this is a very good current buffer. It will take a current input here and will put the same current here. But here the input impedance is small, is 1 over GM, and here the output impedance is large, is GM times R naught times RS, is approximately that. So a good way of remembering this is if this is RS, then GM R naught, which is the intrinsic gain of this transistor, GM R naught, is multiplied by RS, and then we have the resistance looking into that port. And this is, as I said before, a good current buffer. It will take a current and it will give the same current but with higher output impedance. Then we have the common drain amplifier, which is the opposite. It's a good voltage buffer, which takes a voltage with a very high input impedance, and it will give us pretty much the same voltage, but with a very low output impedance. In this case, 1 over GM, and I control GM by this current. Okay. Well, these two voltages are not exactly the same, right? So there's a big difference between these two. This is VI, and this is usually VI minus VGS. So why did I say that this is a good voltage buffer? Because it's for signals, right? We care about signals. Usually amplifiers work for small signals, and we don't care much about DC. Then the input and the output are the same, except for a DC difference, right? Okay, so this is a summary. Use with care because many things change when you load the amplifier. Okay, quiz. What kind of amplifier is this one here? And does it really work? And does it have any advantages over? So, okay, here's the input. So I would say it's not a common gate, right? Because the common gate has a current input, and this is a voltage input at the gate. So, but it's, oh, and this is, okay, if this is an NMOS device, then the current flows this way. So this is drain, and so this is a common source, right? But why do I have this current source here, and what does it do here? Well, basically, this amplifier is the same as this one here. But in this case, we need to provide this a very precise VGS to have this transistor in the operation region we need. In this case, this current source will make sure the current here is ID. And VGS will be anything to make sure that this ID is in this transistor. And why do we need this capacitor to ground? this bypass capacitor. We want the signal to go to ground somehow, right? If we didn't have this, the current would be just this and we wouldn't have any signals. So this one will basically connect to ground. So this in signal is a very small impedance, right? So it's a decoupling cap. Okay. Current mirror. This is a very important topology. Basically, what I do is I have certain current over this device, which is connected as a what? As what we connect this device? Diode. Very good. So we connect this as a diode, and we have it. This becomes a two-terminal device, right? So we have a VGS that will hold the equation. So basically, this solves this equation and gives me the VGS I need for this current, okay? And then this VGS is copied here. So what happens to this transistor? It will have the same current, pretty much. Not very, very, very same current, but pretty much the same current. What differences? Well, there are some differences due to VDS because they won't necessarily have the same VDS, but there are some ways to solve that problem too. Okay, we can use current mirrors for simple biasing, right? So we can make a current mirror based on PMOS device and use that as, in this case, as a active load. Differential pair. This is another very important block. Yeah, so why is this so important? Because the differential pair allows us to compare two voltages and gives us a signal that's proportional to the difference between those voltages. This is the basic equation of the differential pair. And if we operate this for VID over VOV, where VOV is VGS minus VT, if we operate this where VID is small compared to VOV, then this is really, really linear. And if we work in this linear regime, we can use this to make an amplifier with an output that's proportional to the difference between the inputs. That's the definition of a differential amplifier. So this is the core of anything that looks like this, right? So usually we have these two signals right here. Okay, now we know the differential pair. Active load, I already mentioned a little bit of this. So this transistor with a constant current is basically, if I have the constant current, then the small signal model for this transistor, instead of having a GM times some V, if this V is constant, then this GM goes away, and this transistor becomes just a resistor. And there are many reasons why we want to have an active load. Room, output swing, there's many reasons why we want this to be a transistor and not a resistor. If this is the case, then we have an amplifier made of transistors only, right? So this is the active load. Again, this is not a circuit design course. I'm going really fast on this, but there are many, many good books on this. Cascode, common source plus a common gate amplifier. So here's the common source, right? The common source, the source is the common between in this amplifier, right? So we go back a few slides, and this is, no, I'll say this is okay. This one here. So this is the common source amplifier. This device needs a load resistance, right? So we'll go back here. This device needs a good load somehow. The problem with the common source device is that it has an internal resistance that gets in parallel with the load, and usually that's a low resistance that will make the gain not too good. So we combine this with a common gate amplifier, which we said is a very good current mirror. So any current that this transconductor, that this GM will produce, any current will be passed to the output, but with very high resistance. So this is great. We are increasing the resistance by GM times R naught, basically. And the gain at the end ends up squared from what we had in a common source amplifier. This is great. This is a great advantage. It also has advantages in terms of bandwidth because it's not part of this micro tutorial, but this CGD that will produce a Miller effect that will end up being a problem for high frequency design. In this case, we don't have that because this node doesn't move much because this node doesn't move. And then we have a much faster device at the end. So we get gain without losing bandwidth. That's great. That's great for design. And then we have the folding amplifier, which by itself is not that important, but it's important because I'll show something later. So this is a basic common source amplifier. So the current goes this way, right? But what if we want the current to go that way? We could do that if we put a constant current source here. If we put a constant current source here, there cannot be any AC current here. This is only DC. So any AC current will flow that way. So we folded this resistor down, and this is a folded common source amplifier. This is important because we can also fold cascodes. And when we fold cascodes, as is down here, we get pretty much the same performance of a cascode, but we gain, we get much better performance in terms of common mode issues. Here we have a much better common mode input range. We don't have many headroom problems here. So the folding cascode is a great idea. As I said before, this is our review. This is an overview. This is not on circuit design. Okay, come on. So how do we compute the gain in this case? Well, I'll tell you a hint. Actually, the in is here, and this is another part of a differential pair, and this is a current source, and this is another differential pair, and they're connected somehow to this folded cascode, and this is a class AB output, and these are floating batteries that will hold this working in the bias I want, and these are compensation capacitor and nulling resistor, and at the end I have a circuit that I cannot compute the gain again. But we can compute the gain of this, okay? So if we put this into first stage, second stage, we do this for first stage, we do this for second stage, and we have gain that we can compute. Actually, the gain in this circuit is 1, because it is an operational amplifier connected as a follower. So the short answer here is 1. Okay, the closed loop gain is 1, but we can compute the open loop gain of this if we cut this wire here. We can do that, and it's not that complicated, and SPICE can do that for us too. But it's good to know how to do it because SPICE is only a calculator, and we need to know how to design circuits. Okay, how do we estimate bandwidth? In an IC, bandwidth calculation requires deep knowledge on transistor parasitics. So we want to know what parasitics will preclude our circuit from going faster. Usually it's hard to compute when there are many poles involved, but there's a technique, it's a great technique that will make it easy to estimate bandwidth. So we take for each capacitor in the circuit, it could be each capacitor, for example, this transistor has one capacitor here, one capacitor here, one here, it has one from the body, 2, and each transistor has many capacitors. For each capacitor, You remove all other caps, compute the equivalent resistance seen by that capacitor, then you get a time constant, and then you sum those time constants. 1 over that sum is an estimation of the bandwidth. So this is a very simple way of estimating the bandwidth of a circuit. Okay, a single slide on feedback and stability. Why a single slide? Because this is a very, very important topic. I cannot emphasize enough how important this is. And I cannot see it in this tutorial because it would take too much time. So I will say a few things about it. Feedback controls the gain of an amplifier. It increases the apparent bandwidth. It doesn't change the bandwidth of the circuit, but it reduces the gain, so the apparent bandwidth is much higher. And actually, we use that bandwidth. We reduce noise, we improve linearity. It has many, many advantages. But feedback can cause instability, particularly for multi-stage amplifier. So we need to learn to do this loop gain analysis to make sure that it's going to be stable. If you don't do that, you will end up with an oscillator. Don't ask me why I know this. Okay, sizing and biasing of transistors. Transistors are sized and biased according to their function or performance, right? A narrow transistor with a lot of current is fast. It has a high VOV, overdrive voltage. A wide transistor with a small current is efficient. It has low VOV. A long transistor has lots of intrinsic gain. So how do we want to bias and size transistors? I know the equations, but we already said that equations are horrible. So we don't want to use the equations. Also, short channel transistors don't obey these equations, right? So we will give a hint on how to size transistors. There's a few figures of merit for any one transistor that we use. We want a lot of GM without investing a lot of current. So we could say one figure of merit is how much GM per unit of current I get, GM over ID. We want some GM without introducing too much capacitance. So another figure of merit is GM over CGS. And we want to know, of course, the intrinsic gain of this transistor, GM over GDS, where GDS is 1 over R0. So these three are our transistor figures of merit. If we use long channel equations, square law equations, low field equations, we get to these three expressions that are very simple to obtain. VOV, as we see here, trades power efficiency and speed, right? If we increase VOV, we lower this power efficiency, but we increase the speed. But we also lower the gain. It's like a knob. So VOV acts as a knob that we can use to tune the performance that we want from a transistor. So VOV is the knob, right? We increase VOV, we get more FT. With FT is actually related to this figure of merit. And we get less GM over ID. And our job as IC designers is to define VOV to get enough bandwidth and minimize power. L matters, but I will mention this. We are a little bit short on time. So this is a summary of figures of merit. Current efficiency, transit frequency, which is, in this case, omega t, which is related to ft by 2 pi, and then intrinsic gain, which is this one here. Any device in any technology can be characterized according to these figures of merit. And the long channel equations are really bad. If we simulate GM over ID, we get this, while the equations predict this. It doesn't look right. Here, they are reasonably accurate. Here, they are not. Here, they are too far, right? So why? Why they're so different? Okay, this region here with high VOV is strong inversion. Here, the MOSFET behaves as a MOSFET. with the square law and all that. Then we have a weak inversion operation here. So this is weak inversion, where the MOSFET doesn't follow the equations that well. And here we have a subthreshold operation. And the MOSFET actually looks like a BJT here, this part. So this is more a BJT than a MOSFET. So we can simulate FT, and we will find differences. The model expects this. At the end, we get this other thing here. Again, it depends on VOV2. The long channel model no longer holds, right? And then we simulate the intrinsic gain, and we see that they are quite different. So how do we design? How can we use equations at all? We cannot use equations. The gain, this is the intrinsic gain, depends on VDS. So if we plot the intrinsic gain for VDS, we get something that changed a lot, and we want to use it with high gain, but if VDS is too small, we get into this region of small gain, and if VDS is too large, we get into this other region with small gain. So, so how can we design a chip if we don't have good equations? Well, there are some models, but they are too complicated for design, right? So what we will do at the end is that there are great difference between hand models and SPICE, and the long channel model is not good. So it fails to predict the current efficiency, the transit frequency. Sorry, I made this on an airplane last night. Frequency and the intrinsic gain. So it does not predict what happens in the subthreshold region. So what happens in subthreshold region? Okay, we see again this transistor. We have this N plus P type substrate. And then we see that this is not that different from something that looks more like this. Is it? Isn't it? Yep. Yeah, a little bit, right? NPN. So what is this? We have a BJT. So there's some kind of parasitic BJT here. And this transistor in subthreshold operation behaves more like a BJT than a MOSFET. When it's almost off, this transistor works as a BJT, as a very bad BJT, because it also has a capacitor in series. So it's a BJT that kind of works, but doesn't work that well. So on a BJT, we have this equation. On a BJT, which is a parasitic BJT in a MOSFET, we have the same equation, but this term changes, and there appears an N here, which makes this not that good. So the BJT, the MOSFET at very, very low VOB becomes BJT. So we see that we expect this, but we get this. And this is like a BJT. Here it operates as a BJT. So GM over ID, instead of increasing a lot for low VOV, kind of stays the same, which is the case for BJTs. In case of BJTs, GM over ID is 1 over VT. We can get to that result very quickly. So doesn't work that well. Oh, I had the plot here. Sorry about that. Yeah, so GM is ID over VTH, and GM over ID is 1 over VTH, basically. So we can't get past this line here. So long channel models are not good. So what can we do? And the easiest way, I think, to design a chip without good equations is using SPICE-generated tables. So we make a table, or we draw curves that show how the transistor works. Spice models are usually very complex. They have hundreds of parameters. We can't really design with a Spice model. So what we do is put this into Spice. Spice gives us curves. For example, this one is ft for GM over ID. As I increase GM over ID, ft decreases. And I can use this curve. For example, if I want ft to be 1 gigahertz, I will use a GM over ID of 15. And I can use this curve for any length I want. So I draw these curves for different transistor lengths, and then I use the one that's best suited for my design. I do the same for PMOS, and I do the same for intrinsic gain. So I draw intrinsic gain for different GM over ID, different lengths, and then I know what to expect from each transistor. I do the same for PMOS devices, and then I need to complete this design somehow. So I will do a current density plot. This current density will say ID over W. So this is the current density, how much current per unit of width in a transistor as a function of GM over ID. So if I want this point here again, using GM over ID equal 15, I need to have ID over W equal to 1. I do the same for PMOS devices, and then I know how to design a chip. So this is a suggested design flow. According to this design flow, we specify the transistor according to the required performance. We don't do it according to the size. So the size of the transistor is a consequence of this design flow. We begin with specifications. We say we want certain GM over ID, certain FT. Then we size transistors, and then we verify. And we iterate as many times as necessary. There's an intuitive point of view, which is if we split this transistor into two, we have two transistors in parallel. Both have the same current density. Each one of these have the same FT, right? And so FT doesn't scale, so if we put them together, we have the same FT, and so on. Yeah, I need to hurry up a little bit. Noise, I won't say anything about noise because we're too late now. Mismatch. Well, sometimes we need very well matched components. For instance, input transistors in a differential pair, we want them to be the same. Or passive components in a feedback configuration, we want them to be the same. So we want them to be very well matched. They are better matched when they are big and they are close. That's the deal. We want them to be big and close. Mismatch calculations are done according to Pelgrom coefficients, which are these coefficients here, which are sometimes provided by the factory, by the fab, and we can calculate the standard deviation on a certain parameter, for example, on VT, according to this equation. And on data, same here with this equation. So here's an example for a certain technology where the coefficients are 10 millivolts micrometer and 1% micrometer. We do the calculations for a 20 micrometer width transistor and 0.5 micrometer long, and we get 3.2 millivolts standard deviation on VT for this size. So we can compute the standard deviation of VT with this simple equation. And this depends on the transistor size. We want lower VT, we need to go with a larger transistor. We can't afford such a large transistor, well, we have to compensate digitally or something else. There's another layout, there's a layout technique, which is a common centroid technique. So basically, if we want two transistors to be very well matched, what we need to do is to split these two transistors, for example, transistor A and transistor B into two halves. And we connect these two in parallel, these two in parallel. The center of this transistor, I would say it's here. And the center of this other transistor is right here. They share the center. So this is a common centroid technique. And if they share the center and they are symmetrical, they will behave well when there are gradients in the process. If there's any gradient that will make stronger transistors to the right and weaker transistors to the left, this technique will prevent that, will prevent the mismatch between these transistors. Okay, let's go with layout. Again, what's layout? It's the physical description of each one of the chip components on every layer. So this is what we want to get to, right? We want to design a chip, we want to end up with a layout. Can be done fully automatic based on standard cells, or can be fully customized, or can be a mixture of both. And we must obey the rules. So what's standard cell layout versus full custom? This is a standard cell. This comes from a PDK, and we can use standard cells, put them together, one next to the other one, and then we end up with a digital design. This, as opposed to that, is a full custom cell. This one here is a full custom. This was done by hand. So we here see cross-squatting. This and these transistors are cross-squatted. They share the same centroid. Same for these two here. And there are some other transistors here that are fully made by hand. This is a this circuit is a comparator. This is a voltage comparator with a latch. It's a latch comparator. Okay, topology. We know that the IC has transistors, interconnections, resistors, and capacitors. Most of the IC surface is covered by interconnections and passive elements. Transistors are usually small. And here we have the layout, and here we have the cross-section. So again, this layout, we see a transistor, an NMOS, then a PMOS on an N-well, and we here see some interconnections. So when we do a layout, we use layers. We use different layers, right? We use, for instance, polysilicon for the gate. So that's one layer, polysilicon for gate. Then we use N diffusion to make NMOS transistors. We use P diffusion to make PMOS transistors. We use metals for interconnections. And there are some other very important layers. Here we have contacts. This will go from one layer to another layer. So this poly contact will connect poly to metal 1. ND contact will connect N diffusion to metal 1. So it would be this one here, right? It will interconnect between metal layers. And that way we have many, many layers. And we have to paint the design. We paint it. We have 4 possible diffusion combinations, and this is something that we have to know if we want to design a chip. We can have P plus over P sub, P plus over N sub, N plus over P sub, or N plus over N sub. All right, so P plus over P sub. What does this mean? This means P plus diffusion over a P substrate. So P plus over a P substrate. When we get that, this is P substrate, and P plus, this is P plus over P substrate. That will give us a ohmic contact to the substrate. So that's what we do. P plus over P sub is an ohmic contact to substrate. This is the chip substrate for the whole chip. P plus on N well. This is something we have seen P plus over N well. Remember, this is N well, and this is P plus. So this is part of a PMOS transistor. We go here. P plus on N well is a PMOS device. It's part of a PMOS device. Then N plus over P sub is for an NMOS device, and N plus over N well is the connection to the N well. It's an ohmic connection. If we know these four combination of diffusions, we can be ready for design. Some restrictions on design. So there are two important restrictions: resolution restrictions and alignment restrictions, and they are all covered by design rule check, or DRC. So we have this software that will check for rule violation. These are known as design rules. There are tens of them. They are defined by the fab. It's good to get some familiarity with these design rules. It's not necessary to learn all of them, but it's good to know at least a few of them. We will skip this. Some other restrictions for layout. NDIF and PDIF cannot touch. If they touch, it's a violation of the rule, right? They're in different substrates, so they cannot touch. N diffusion and P diffusion cannot be very close, right? There must be a minimum distance. This is another rule. So we group all NMOS devices together and PMOS devices together. I'll go back to this slide here. And we see here all of these are NMOS. And all of these are PMOS devices. And they all share the same substrate, or the same well in this case. So we put them in different regions. Finger devices. Okay, what if we want to make a long transistor? There are chips that require long transistors. One of the things I do is instrumentation for particle physics experiments. And then, in that kind of circuits, you need long transistors. It's common to see transistors that are 2 millimeter long. You can see them, actually. 2 millimeter, that's a huge transistor. So how you fit that transistor, and the way of doing that is with finger devices. Basically, we cut this into a few fingers, and we put these fingers, we put this device together. For instance, if this is source, drain, source, drain, source, drain. All drains are in parallel, all sources are in parallel, and the gates come all together. So this, you see, it looks like fingers, right? So this is a finger device. Finger device have a lower gate resistance, so they might be faster in certain circuits. And you can shape them as you want. Some more recommendations. When you are designing any wire, any interconnection, think that as if you were an electron in a marathon of electrons trying to get to VDD. Many of them, right? Many electrons, and you want the easiest path, the easiest way to get to VDD. Always talk to the circuit designer. If someone else designed the circuit, talk to him or talk to her. What's the circuit function? How much current? What devices should be matched? You want to know that. What needs to be shielded? Oh, this is cool. You can use metal layers for shielding purposes. You can shield devices with a Faraday cage. You can do that with just metal. That can be done. That's usually done. And you want to know what should be shielded. Be careful about high currents. Be careful about parasitic capacitances, parasitic resistances, and parasitic inductances. Sometimes you can use wire bond inductance for making good RF circuits. More recommendations. M1 horizontal, M2 vertical. So you draw metal 1 and metal 2 like this. And guess what? Metal 3 goes horizontal, metal 4 goes vertical, etc. That way it's much easier to route. Always have matching in mind. Um, Careful about symmetry. These are many things that may sound a bit like common sense, and they are actually common sense. So you require a lot of common sense if you want to design a chip. So how to prevent E&M noise and interference? One way is to put shields on top of transistors, but there are some other ways to prevent substrate noise, which is using guard rings. Guard rings are rings, right? This is a ring around a transistor. So this is the transistor, and it has a ring around it. So this is an NMOS transistor. This is the gate. This here is the drain. Here is the source of the transistor. And here is the substrate. So this is a body connection. This goes to ground, right? And the substrate is around this transistor. So again, here we have a P sub, and this one is a P plus sub. Then we can put another guard ring around it, an N plus guard ring around it on an N well. And if we do this, we have this region is N, this region is P. So we have something like a diode. This looks like a diode, and usually diodes don't let current one way. So this works as some way to prevent substrate current to add some noise on this device. Okay, more recommendations. Leave room for regret. Always leave some extra room because you might use that later. If it looks good, it will work. Well, that's also, remember, DRC, LVS, etc. Make copies of cells before modifying them, and divide and conquer. Start with small things and then put them together. Distribute supply in a solid network. Make sure that every transistor gets good supply. And now we go to design tools. So again, mainstream developers are Synopsys, Cadence, Mentor Graphics, Tanner. There are some free tools, Electric VLSI, and Open Circuit Design. This is one we have been using with reasonably good results. So I'll show a few things about that if we have time. Fabrication services. So there are multi-project wafer runs. MOSIS has an educational program. So MOSIS takes designs from different clients and submit them for fabrication in a single wafer. So they make a wafer with many reticles, and in each one of these reticles, there's one from Chile, there's another one from Brazil, there's another one from Argentina. There's many chips. So they are diced later and submitted to the different designers. MOSIS has a program, the MOSIS educational program, which is free for academic institutions to fabricate chips through MOSIS for a restricted size, a restricted process. But still, you can do that. In our university, we are actually submitting and testing chips for an undergrad course. We do that regularly. The usual requirements to start working with these are NDA signatures. Sometimes they take a lot of time to get, right? Sometimes they are quite difficult to get. But once you get the signatures, you are set and you can design for that technology. EDA tools, sometimes they are hard to get. In Chile, we don't have cadence, and maybe we will have cadence fairly soon. But at this time, we don't have access to cadence. So it takes time and effort to set up a design flow that works. But once you have it, you can design chips with that, and it's reasonably easy. Some more resources. This is just an overview of the courses that we offer in the institution where I work. And this is as an example of some microelectronics program that is not that difficult to set up, and it works reasonably well. And here's some reference that I want to have some time doing something else, which is showing the actual design tools. So we will run Magic. Okay, Magic is the program, an open source program that is supported by Tim Edwards on this webpage, Open Circuit Design. And so here's how we design chips with Magic. So we start with a substrate, which is everything that we see in the back. And then we put some N diffusion, and we put some poly on top of it, and we have a transistor. That's a transistor. And then we need to add some contacts. I don't know the rules at this time, but yeah, so it's okay. If I get closer, I will see something that it doesn't like. No, it didn't like it because that thing we see there is a violation of a rule. Now we're not violating the rule. So if I do the same here, I have a transistor. And then I have a gate, and we want the gate contact, which is this one here. And we have a transistor. That's a transistor, exactly, yeah. And then we have a metal layer here, and we can route this as we want. And we can do whatever we want with this. And we have another metal layer here. And we can actually cross these two with another metal here. We will use metal 2 here. And this is connected through here, M2 contact. So, whoops. There we go. So here we have our transistor, and yeah, and these two are not touching each other. And that way you can actually design a chip. It takes time, of course, it takes time. I'll show you another layout. I don't remember which one is this. I think it's, yeah, it's this one. So here I have 3 amplifiers. And if we look, they are the same amplifier, copied 3 times. And if we get closer, we see the actual amplifier with the transistors. Here's a violation, design rule violation, but I don't care about this because it's because we are using hierarchy, but we can prevent that from happening. Here's a capacitor, a big capacitor, and actually that's the way you just design a chip. This is it. It's no more complicated than this. Yeah, it looks like PCB, but each transistor is something you draw by hand. Yeah, that's how it works. But it's not that complicated. And if you go to MOSIS, MEP, and you read about that, you will see that there's many institutions that are actually designing chips through their program, and you can do that. Anyone can do it. So yeah, that's my final advice. I think we're on time, so I'll stop here. Thank you so much for attending this talk.